All right, so we're going to keep on going with 4-1 today. So we're going to wrap up talking about inverse variation. Then we're going to also look at reciprocal functions like we did in the warm-up a little bit today too. So this one says, on a guitar string, the string length S varies inversely with the frequency F of its vibrations. I don't know a ton about guitars, but as soon as I see the phrase varies inversely, it's telling me that it's got to have this Y equals K over X relationship. Now, instead of the variables being Y and X, in this problem they're S and F. And it actually doesn't matter which one you call S and which one you call F. It's really all the same. So, if you want to call it F equals K over S, that's fine. If you want to call it S equals K over F, that's the same thing. The position of those variables won't change how the problem works out. So this basically we know is the equation. Now we're going to have some numbers down here that we're going to be able to figure out what this K value is. So this says the frequency of a 26-inch E string is 329.6 cycles per second. So here they're giving me the string length S, and they're giving me the frequency. So they're giving me an S and F combo that I can use to find that K value. So in this case, if I just take 26 times 329.63, that's going to give me the K value for this inverse variation. So what's that going to be? Some decimal. Let's see. 26 times 329.63. 8570.38. Okay. So that's my K value, which means then, just taking my equation from earlier, I can basically say my equation is F equals 8570.38 over S. So this is my equation that I can use to now answer the question. The question is, what's the frequency if the string length was 13? So string length is now going to be 13, so all I need to do is substitute that in. 8570.38 over 13. Divide that, and we've got ourselves this frequency. So just take that and divide it by 13, 659.26. And that's in cycles per second, say CPS. The nice thing with this stuff is you don't have to know anything about the thing. Like, I don't know a ton about guitar string lengths and how many times they vibrate per second and what that kind of stuff. But as soon as you know it's an inverse variation, it has to follow this style of equation where you can multiply the two data points together to get the K value, you can write the equation, then you can solve for whatever part they give you. And that's pretty much it. So below this here, there's a similar problem with temperatures. So this one says the amount of time it takes for ice cube to melt varies inversely. So again, as soon as we see this, we know what kind of equation we're dealing with to the air temperature. So here it's time and air temperature. So I'm going to use T for time, and I'm going to use, we'll go ahead and go A for air temperature. So I know my equation is going to be something like T equals K over A. Or I could say A equals K over T. Where the A and the T go doesn't matter. Those two spots are interchangeable in this equation. Okay, so it says at 20 degrees Celsius, the ice will melt in 20 minutes. So they gave me a temperature and they gave me a time. So I know that I can multiply those two values together to get my K. So if I do 20 times 20, that's 400. So my equation for this problem is 400 over the air temperature. All right, so what do they give me? They say, how long will it take for the ice to melt if it's 30 degrees Celsius? So the air temperature is going to be 30. So I'm going to go 400 divided by 30. And whatever that is, that's how many minutes it's going to take to melt. And 13.3 repeating, which makes sense. It's a hotter temperature. We should have a shorter time because that's how things work. So 13.3 repeating minutes is the melting time. So these are story problems with these inverse variation concepts that we learned yesterday. Okay. So the key is I set in variables, setting up the equation, finding the K value, the constant, by multiplying the two values go together. All right, and then the other thing we're going to look at today is this example 4. And this is what we touched on in the warm-up today. So it says, how do you graph the reciprocal function y equals 1 over x? So when it says consider the domain and the range, we talked about this domain. And for this domain, the idea is, and this is how we're going to write these, so you're going to see this a lot in this chapter going forward, is they use a set notation. They say, hey, x can be anything, except like we talked about, x can't be 0. So this is how this notation looks. I'll kind of walk you through it once we once we get it written down. So they put these little set notation brackets around it to indicate that, hey, it's a set of numbers. Then the way you'd read this, you're saying x can be anything except x cannot equal 0. So it's a notation thing where they're saying, here's the variable, and here's the things that it can't equal. If you remember what this graph looked like, we can go ahead and sketch it on here. We'll talk about domain in just a second. But if you remember this graph had this shape to it, right? From the warm-up today. And I can throw it in my calculator too, just so we can see it again real quick. But if I put it in there and I graph it, there it is. I'm not drawing a super accurate graph here. I'm not like plotting specific points or anything like that. I'm just kind of looking at where it's at. But again, the range is actually really similar. When you say range, you say what numbers can we get out? You also can't get 0 out of this function. This graph approaches 0 but never touches it. Same thing here. So for our range, which is the y values, we'll never get 0 either. And that's why there's both a vertical and a horizontal asymptote. I know we defined it on the warm-up, but I think it's worth defining here is this concept that it's talking about. It says observe the graph as it approaches positive and negative infinity. So as this graph goes towards infinity, as it goes out here, the graph itself approaches 0. And as you go towards negative infinity, this graph also approaches 0. So it says observe it as it approaches infinity to negative infinity. We'd say that y approaches 0. In other words, we could say the x-axis is an asymptote. So that asymptote term, just again to clear it up for you, is when you have a line that the graph approaches but never touches, which is what's going on right here. This says, what happens to this graph as x approaches 0? So as your x values get close to 0, this graph starts spiking upward. And as you approach 0 from this side, this graph starts spiking downward. But again, it never reaches 0. So what we say is this graph either goes to negative infinity or it goes to positive infinity. So we'd say y approaches positive or negative infinity. And according to this, the y-axis is an asymptote. And any of these graphs that we look at, we're going to see a bunch of these over the next couple of days, is going to have asymptotes. Ours happens to have 2 asymptotes, one horizontal, one vertical. You're going to see all kinds of combinations as we go forward. But that's the basics of it. The other piece for today is we're going to start getting into talking about transformations a little bit. And so this says graph this function, which is the same exact thing, except now it's 10 over x. So the only thing we're changing here is we add in, make it, not 0, 1, 1, 0. So we put in 10 over x. If we graph this, what you probably notice is it doesn't look a ton different. So remember what this one looked like. If I went back and I also put in 1 over x, so 10 over x is already on there. 1 over x is just tighter to the axes. So all that happens when we increase the number is the same thing that's happened every time we've increased a number like this on any graph, is it stretches it. It makes this graph go further, it stretches further out, like away from the origin. So whereas this one was pretty tight to the origin, this one's now pushed further away. And that's what that 10 is going to do. So in terms of what does this 10 do, if you remember, we're going to say this graph has a stretch of 10. Remember that term from chapters 1 and 2 and 3. We've seen that a bunch. And then it follows up with all these same other questions that we talked about in that one. So let's just go ahead and answer these. The domain, same thing. X still just can't be 0. You can't put 0 into this because you can't divide by 0. So same notation we used earlier. We'd say x, where x cannot equal 0. And then for our range, if you notice, we run into the same issue. So whether you look at it on the graph, the calculator, whatever, this graph still approaches but never touches either of these axes. So in the same regard, our y value, we never get 0 either. Which leads perfectly into the questions about where are the asymptotes. So we would say this graph has a vertical asymptote. Vertical asymptote would be the y-axis. Now, one thing to keep in mind here, the equation for the y-axis is actually x equals 0. It's the line where all values were x equals 0. So remember that. We're going to see that a lot in the kind of the next day. And then we also have a horizontal asymptote. Remember, asymptote just means it's the line the graph approaches but never touches. In this case, these are approaching but never actually reaching the x-axis. And the x-axis is actually, the equation for that is actually y equals 0. It's the value where every y value is 0. So it's just a flat line across here. So that's what we're going to see today. So we got the inverse variation stuff from earlier, plus just the basic graphing of the reciprocal function. We'll get into transformations and stuff of it tomorrow.